Hello, everybody, and welcome to another wonderful day of chemistry. So, today we're going to be talking about chemical elements, which is going to include both how we can differentiate different types of chemical elements, but also the variety within elemental species, mostly based on overall charge and the number of uh, neutrons present, which actually brings us to the first important question, which is really how can we tell the difference in between different elemental species? And we kind of alluded to this last time, as the predominant feature that controls what type of element a given atom will be is the number of protons. If an atom has one proton, it's going to be hydrogen. If it has two protons, it's going to be helium because the number of protons will dictate the overall nuclear charge, which will in turn determine the number of electrons under nuclear conditions, and thus the overall reactivity. Because in general, we assume most systems are going to have a neutral charge, and under those cases, electrons equals protons. The other important thing to keep in mind is that while a given element will have a certain number of protons, the number of neutrons can actually differ. And this means that most elements can have multiple different isotopes or overall number of overall atomic weight based on the number of neutrons and protons present. If a species has for the way we describe two species with different with this of the same element with different numbers of neutrons is we call them isotopes. So isotopes are mostly going to be denoted by their overall atomic mass, or again, that combined number of protons plus neutron. So one of the great examples of isotopes that you'll occasionally run into, and is so important that we give each isotope its own name, is hydrogen. So if I have a hydrogen atom, it just has a single proton. However, if I have deuterium, this is an isotope of hydrogen where we have one proton and one neutron for an overall atomic mass of 2 AMU. Where AMU is atomic mass units, it's another way of just saying how many nuclei are present. Uh, and then we also have the much rarer tritium, which is one proton and two neutrons for a total mass of 3 AMU. It is worth noting that tritium is fairly unstable and is mostly found in nuclear reactors. And if you ever hear people talking about things like heavy water, all that really is going to be water where we replace the hydrogen atoms in water with deuterium atoms, which has slightly different behavior. So when we're talking about these elemental species, it is going to be possible to convey all of this information in a single combined symbol, which is dominated by three key characteristics. The first is going to be the atomic number. So this is often referred to as Z, and this is just simply the number of protons. So a given element is going to be defined by the number of protons present. So if I've got carbon, it always has 6 protons. The next one is the atomic mass number. It's often represented by the symbol A, and this is just simply going to be the total number of protons and neutrons. This is also going to be the same as the mass of that given isotope in AMU, or atomic mass units. So again, just protons plus neutrons. So if I have, say, carbon 12, which is the most prevalent form of carbon, it will have 6 protons and thus 6 neutrons to make up the difference. You also find species of carbon like um, such as carbon 13 and carbon 14, which are often used to do things like radio date carbon, as their ratios are often determined by A, the age of the sample, and B, the source of carbon in the thing you're dating. And again, when we're talking about AMU, the official definition of AMU is that of a single mass unit is that one AMU is 1/12 of the mass of a carbon 12 atom. And since carbon 12 has a total of uh, 12 protons plus neutrons, this means that one AMU is approximately the mass of one proton or neutron. But since these masses are slightly different, it's a way to kind of refer to an average mass of protons and neutrons. The last major feature here is given by the symbol X, and this is essentially our chemical symbol. So you'll run into these any number of times in everyday life, and it's just simply a 1 or 2 letter symbol that references the element being talked about. So, for example, carbon is C. So many of these are actually based on English because, thankfully, uh, English speakers have helped name a lot of different chemical species. However, that isn't true of all of them. A lot of older elements, especially, are based on a Latin name. So, for example, you have one of the oldest elements out there, silver. Its Latin name is argentum, so it's given a symbol of Ag. You'll also find other species that this is true of, such as gold or Arentium, which is given a symbol of AU. So if something doesn't make sense, it can often be useful to try and figure out what the original Latin name of the element is to help explain the 2 letter symbol. Now, one of the reasons why it's very useful to have a condensed form or description of all of this elemental information is because we can combine that into the wonderful item that is the periodic table of elements. So the periodic table of elements simply is a way to arrange all of the chemical species based on reactivity. And we'll be talking about this much more later. But you can see that most of your periodic tables will contain a series of crucial information about each element present. So let's go ahead and zoom in here on potassium. So in this form, we have a lot of the same information we saw previously, just in a slightly different form. So we have the atomic number of the element here up top. So potassium has 19 protons. However, it has an atomic mass of 39.1. Now, with an elemental symbol of K. Yes, guess what? This comes from a Latin name. However, one of the big things I want to focus in on here for a quick moment is that atomic mass. Because you'll notice that this atomic mass is not going to be a whole number. And the reason why is because when we're reporting atomic masses on a periodic table, we're not talking about a single isotope. We're talking about an average of a whole bunch of isotopes that occur in nature. So if I were to essentially take the average atomic mass of potassium in nature, it will have a mass of 39.1 because there's multiple different isotopes present. So let's go ahead and work a more concrete example here for potassium. This is actually not too bad because potassium has 2 different isotopes. It can either occur as potassium 39. So this would be where I have 20 neutrons, or as potassium 41, where I would have 22 neutrons. However, over 93% of potassium is 39, while only about less than 7% is potassium 41. So it isn't too surprising if I go out in nature and I take the average atomic mass will be a lot closer to that 39 than it will be to the 41. So we can actually calculate this directly by taking the mass, by calculating the average mass as the mass of each isotope times its natural abundance, and then adding these together. So when we do this, we end up producing the experimental value of an atomic mass of 39.1. So I do want you to make sure to note the difference in between atomic mass and nuclear mass, which would again be for a single isotope. However, one of the other important things to make note of is just like not all atoms of a given element will have the same number of neutrons, not all atoms are going to be neutral and have the same number of electrons as protons. Because remember, we have these protons and neutrons sitting here at the center of an atom. So it's going to be really hard to gain or lose a proton or a neutron. They're all too tightly packed and they're very and they're very far away from the exterior of the atom. However, electrons are moving at very high speed, fairly far away from the nucleus. So it's a lot easier to gain or lose electrons. This is going to dictate a lot of chemical reactivity. However, if a electron is gained or lost, we generate an ion. And this means that I have an element with an overall charge. So we can calculate this charge as the total amount of positive charge minus the total amount of negative charge. So if I have more electrons than protons, I should have a negative charge, which agrees with the negative nature of an electron. If I have more protons than electrons, I should have a positive charge, which again should make sense because of the overall negative nature of electrons, meaning that I'm not negative enough, I have a positive charge. So what we can do is take our symbol that we generated for a given atom of the letter symbol, the atomic mass, and the nuclear charge, and we just add in an extra feature here on the upper right as a superscript of plus if it's positively charged, minus if it's negatively charged. You can go ahead and put a number behind that if we have multiple positive or negative charges. So as chemists tend to do, guess what? We have a series of nomenclature behind all of these various ions. So let's say I have an atom that gains an extra electron, so it has more electrons than protons. We tend to call this an anion. And this means that we essentially have an excess of electrons and excess of negative charges, which gives me an anionic behavior. So if I ever talk about an anion, we're looking for something with an overall negative charge. Alternatively, it's also fairly easy for atoms to lose electrons, and if they do, they gain a positive charge and are called a cation. Good way to try and remember this: cat ions have positive charges. Yes, the puns come thick and fast here in chemistry. And essentially, this lack of negative charges allows that positive charge to dominate. Now, one of the things to make note of as we go forward is that some elements are more likely to form an anion, and some are more likely to form a cation. And some elements don't like forming an ion at all. And so in order to try and get an idea of the behavior of a given element, we're going to really want to dive back into that periodic table, which we'll take up next time. Until then, take care.